I'm Lila Cheek, and this is Lab 2 for Physics 2. Introduction. The purpose of this lab is to investigate how distance affects magnetic field of a small bar magnet. This is done using a magnetometer app and measuring distances from the phone that the magnet needs to be to produce different values of Bx. Then these results were compared to a computational model of the same situation. The fundamental principles of this lab is the law, which has the equation that relates magnetic field to direction and proximity to the magnetic object. This is a derivation of that we'll be using in this lab, where N and K are both required from a graph that we make from the data. Then we have magnetic field due to a dipole, which is this equation. We also need to know superposition, which is that the magnetic field is equal to all magnetic fields that are involved added up. So in this lab, it's the magnetic field due to the Earth as well as the bar magnet. So to do the experiment, we had to use tape to find the position in our phone where the magnetic field was being tracked. And then we have a position from on the x-axis and the y-axis to find the distance d in between the magnet and that point, and then we use that distance in our data. So this is the on-axis data. R20, R140, R260 mean that this value right here after R is the Bx that we need. So this is as close to that value that we could get it, and then this is the average R in between those, so how far it had to be away to create that value. And then this is our on-axis graph. As I said before, we use this to calculate R and N. So this is R, and then E to the this is K. So that means that the dipole moment that we calculate from this using this equation is 2.233. And this is the off-axis data. It's a similar procedure. And then we found that D perp is 0.18, or average of 0.18, and that's what we'll be using in our computational model. So the code is here. We have our constant, we have mu, which we just calculated 2 slides ago, and then we have this function that creates a magnetic field using mu and R. This is the equation that was shown on the first slide, talking about the fundamental principles. Then we had to set up a bunch of vectors. So first we created the vectors for the observation locations here, and then we created vectors for the on and off axis magnetic fields. First two are on axis, the rest are not. Then we plug in d perp from the off axis slide, and then we created a magnetic field based on that data and an arrow to represent it. And this is the model it creates. So these are the arrows, and this is the magnet. So we found B at 45 degrees from the model, which is this, is 5.047 times 10 to the negative fifth, 1.14 times 10 to the negative fourth, 0. The B at 45 we got from our experiment was basically negative 9 times 10 to the sixth, 2 to the negative 6, and then negative 4.7 times 10 to the negative fifth. So what if, in the experiment, you oriented your setups so as to compensate for the magnetic north? What if you hadn't done that? The values that we found, such as K, N, and mu, would have been different because they would have been calculated based on VNet that included the Earth's magnetic field as well as the bar magnet. So basically, instead of just compensating for the one magnetic field that we need, we would have included an extra magnetic field. And then second, what if, imagine you had 2 identical magnets. What if you redid the experiment that instead of using a single magnet, used 2 identical magnets stuck together end to end? How would you expect your experiments to differ? Basically, the magnetic field the magnitude of that would increase, but the direction would stay the same because you basically just have a stronger magnet.